This is Alejandro Molina from the University of Murcia in the demonstration of the BMS.2, an insider attack on the fire suppression system. First, we will see a network authentication and device registration through the IoT bootstrapping. Once the IoT device has connectivity, an insider attack tries to activate the fire alarm using a co-op message. Then, the IoT device detects an unauthorized actuation and it notifies to the monitoring modules. The monitoring modules analyze and correlate the event, and then a security alert is sent to the reaction module. The reaction module then generates a new medium-level security policy in order to enforce the countermeasures, which in this case they are the IoT HoneyNet and the transparent traffic forwarding. Here we can see the whole picture for this scenario. First, the security administrator must allow the authentication traffic for the IoT domain so that the device is able to perform the IoT bootstrapping. Once the IoT device has been authenticated and it has connectivity, the attack starts. Then, the monitoring modules detect the issue and then generate the security alert. Finally, the reaction module generates the new security policy in order to deploy the new VNF and the new networking rules through the security orchestrator. Regarding the bootstrapping process, first, the security administrator allows the authentication protocol, the PANA protocol, by a high-level security policy, HSPL, through the policy editor tool. This high-level security policy is refined into a more detailed medium-level security policy, MSPL, through the policy interpreter. Finally, the medium-level security policy is translated into final configuration for the specific infrastructure, which in this case is the SDN controller. After the authentication, the IoT device is allowed to use the network, and we will see how the IoT controller is able to reach the IoT device. Here we can see an example of high-level security policy, which indicates that PANA, which is the IoT domain, is authorized to use PANA traffic against the PANA server. And this is an example of a medium-level security policy, which indicates that we need to forward the PANA traffic from the IoT domain to the PANA server. This is the bootstrapping demonstration from the point of view of the ANASTACIA framework. This represents the ANASTACIA framework. In order to verify the connectivity, this is the IoT controller. This is the SDN controller with the SDN flows, the policy editor tool, and the IoT controller API. At first, the IoT device has not connectivity, so the security administrator models a high-level security policy in order to allow the authentication traffic. Then, this HSPL is refined in one or several MSPLs. And finally, it is performed the policy informant. Here we can see that the SDN controller is allowing the PANA traffic and how it is allowing the IoT traffic after the authentication, so the traffic is allowed. Finally, we can see that the IoT device has been registered successfully. So this was from the point of view of the ANASTACIA framework, and this is from the point of view of the IoT device. Here we can see the IoT device, the PANA server, the IoT device log, and the IoT broker log. At this point, the IoT device starts the IoT bootstrapping against the PANA server. Actually, we can see the exchange of messages, and finally, the IoT bootstrapping has been completed. So, the IoT device already has connectivity, and then the attacker tries to activate the fire alarm by sending a co-op message. The IoT device performs a token validation. It detects a forbidden actuation and it notifies the issue to the IoT broker. In this demo, first we will see an example in order to show that the fire alarm is working properly. The IoT device is running a co-op server. Then we send a co-op message which includes a capability token. The IoT device verifies that the capability token is valid and it turns on the fire alarm. Actually, we can also repeat the process in order to turn off the fire alarm. Once we have seen that the fire alarm is working properly, now the IoT device receives a request which contains an invalid capability token. At this point, we can see that the IoT device notifies the IoT broker instead to turn on the fire alarm. So, the IoT device sends a forbidden actuation notification to the IoT broker. The IoT broker sends this information to the Kafka broker, and then the monitoring modules perform several processes like aggregation, filtering, and correlation in order to decide that the issue is actually an attack, generating an alert to the reaction module. Finally, the reaction module generates the new medium-level security policy, which looks like this. We need to deploy an IoT HoneyNet, and we can also specify the details about the IoT environment in order to replicate it, including parameters like virtual routers and virtual IoT devices, with its addresses, operating systems, services, and so on. This is the demonstration for the monitoring part. At this point, the Kafka broker receives the forbidden actuation notification from the IoT broker. This notification contains relevant information of the event like the affected IP, the affected port and the event type, the attacker IP and port, the timestamp, the device type and the affected URL. Then the XLCM receives the event from the Kafka broker. Here we can see the event and its information. The XLCM analyzes and correlates this information and also evaluates the risk, confirming that we are under attack. Finally, in the ANASTACIA login service, we can see how the verdict and decision support system sends the alert to the reaction module. Also, we can see how the reaction module generates the new security policy in order to deploy the countermeasure through the security orchestrator. The security orchestrator receives the new security policy and performs the policy translation through the policy interpreter in order to get the final configuration for the NFV manual to deploy and configure the VNF and for the SDN controller to forward the traffic. This is the VNF manu. This is OpenStack in order to deploy the new virtual machine, the SDN controller, and the SDN flows. At this point, the security orchestrator receives the reaction and starts with the policy enforcement. This is the security orchestrator starts the VNF instantiation. Here we can see that the VNF has been instantiated. We can see it in the network topology as well as the instantiation in OpenStack. But we can see that the attacker is still reaching the IoT device. So the security orchestrator needs to enforce the transparent forwarding. Actually, here we can see two new intents that had been included. Finally, the attacker is redirected to the IoT HoneyNet. So this is from the point of view of the framework. And this is from the point of view of the IoT HoneyNet VNF. This is the IoT HoneyNet agent, which is waiting to receive the IoT HoneyNet configuration. Once the configuration has been received, the agent compiles the IoT HoneyNet using the configuration specifications in order to replicate the real IoT environment. Once the IoT HoneyNet has been instantiated, the VNF connects with the virtual IoT border router, and we can see that the virtual border router and the virtual IoT devices are reachable. Actually, if we remove the policy, we can see that the IoT HoneyNet is not reachable anymore. In order to show better what is really happening, we will repeat the process, but in this case using a frontend. So we load in the simulator the generated configuration. This is the same compilation step we already saw before, and here we can see our IoT HoneyNet topology. Then we perform manually the virtual border router connection. We start the simulation and we can see how we are able to reach the IoT HoneyNet. Okay, so this is from the point of view of the VNF. And finally, this is from the point of view of the attacker. This is the attacker. This will be the future IoT HoneyNet VNF. So we generate traffic against the real IoT device. At this point, the IoT HoneyNet has been deployed and the traffic has been forwarded. Actually, we can see how the packet delay has been reducing. If we connect to the new VNF and we inspect what is happening in the network interface, we can see that the virtual IoT device inside the IoT honeynet inside the VNF is the one replying the echo request. And that's all. Thanks for your attention.